Hi there, this is Turgeon here, bringing you physics from afar, looking at F equals ma examples. In particular, we're looking at these archetypes, seeing how these force diagrams might match a given scenario. Let's take a look at number 5. Find the acceleration caused by this angled force. Now, we are not told what's happening here. We're only told that we have this angled force, and I hope you can see this on my phone video. The real takeaway here is that I want you to, when you see an angled force, I want you to immediately think about components, breaking that into those pieces of the vector. So we have a 40-degree angle and a 50-Newton force. The way this problem is stated, it doesn't say anything about surfaces or whatever, so I'm just going to do 50 times the cosine of 40. The net force, it says this force is above horizontal, and I'm about to contradict myself because I'm saying find the acceleration, and the assumption in order to solve this is that it's horizontal. We kind of have to, in order to figure out the acceleration, we need to know which way the acceleration is occurring. So if this is horizontal and we get to ignore friction, then I really want to find this tension in the x. So it says ftx. I hope you can see that on the video. So it says ftx. I'm just going to find that. Basically, I'm just going to get that component. So that is equal to 50 cosine 40. And so when I plug in to get acceleration, it's just going to be 38.3 net force divided by the mass of 6. So it's just about 6.4 meters per second squared. Okay, so yeah, fine, there's the answer. But this was the key. The key was drawing the picture. I just want you to see the full picture on this. So let's take a look. If I go in with a bit more detail to draw the full diagram, what we're going to see that is that we have this upward force. This force has components. And then in addition to those components, there is a normal force if it is on a surface. So here's my upward vertical component, and then I also have my normal force. So we have our pieces of the force here. Now notice what's about to happen. I know this is in vertical equilibrium. So what's happening is, for these to be balanced, I know that my weight force is greater than both of those. This is the insight. So that weight force is greater than the upward normal force. This piece is the normal force. And please, please, please don't confuse that normal force with this tension in the y. This is the y component of the tension, and this is the x component of the tension, and this is the weight. This will come into play later. You can see that these two forces add up to equal this. So the force weight is equal to Fy and the normal force together. Now, did we change the weight? Of course not. We didn't change the weight, but what we did was, when you apply an angled force, you reduce the normal force. We can now flip this over and see that the archetype being described is situation B. Situation B right there. But situation B we can go in and we can remind ourselves that we would have components here. Components are added to situation B. So we have two vertical forces, one horizontal force, and we of course have a weight force. So sorry if you can hear my dog barking in the background. Now this is going to be really important as we do problem number 7. You pull a sofa across the floor at an angle above the surface. Okay, now we have friction. So we have all these happening again. We have a steeper force happening this time. Zooming in a bit. And I'm immediately drawing that into components. And then I have this vertical normal force. Look how I take pains to make the normal force not look the same. I'll zoom in on this, don't worry. And then my weight force has to be greater than both, because those two together add up to the weight force. Because when you apply this upward force, which has an upward component, you reduce that normal force. There's also a frictional force, which is related to that normal force. Remember that. So this is friction. And it says U pull. I'm going to call this an applied force because it's U pulling, but that could have been a tension force or something. Okay, so there's my forces with that weight force. All right, now this may be complicated. All I'm really going to do is I'm going to look at these two to get my net force, because I know the acceleration is horizontal. Now think about how I'll explain this. You can kind of pause the video and write some notes down. How do we know this acceleration is horizontal? That's the trick here. How do we know that? Well, we know that because if this is occurring on a surface, this normal force automatically, for reasons we'll talk about later, this normal force automatically adjusted so that everything would be in equilibrium vertically. Again, we have vertical equilibrium occurring. So we have vertical equilibrium because we know that this thing did not, again, hear me out, I'll explain. This thing did not fly off the surface. And this thing did not plow into the surface somehow. So now what you're going to see me do is simply go into some math where I'm going to figure out that force. Yeah, it relates to that force, blah, blah, blah. And I'm just going to do A equals F over M. So the equations are really not the emphasis. The force diagram. The force diagram is the emphasis, so we can find the net force. So everything I do now is just to find the net force. Okay, so I'm going to narrate this and then I'll zoom in on the equations again. Now, a lot of people would prefer to maybe like list all these forces. So my force weight I know is 400 newtons, because that's just mg. Force weight is 400 newtons, m times g. The applied force in the x direction is 220 times the cosine of 65. And that's 92.9. It's almost exactly 93 newtons. The force applied in the y direction, I'm expecting something really close, and it is, so it's 199.4 newtons. Sorry about the focus there. The normal force, if you do some quick math, I know that these two, the normal force and the vertical component, add up to 400, so just do 400 minus that. And so we get 200.6. Oh, now I can do the frictional force, which is mu force normal, which is going to be 0.3 times that. 60.2 newtons. And now I have the makings of a quick solution. So now I can go up here to net force, and I can just say that it's my x component, so my 93 minus 60.2. I'm just doing, if you think about it, I'm just doing that force minus the frictional force, because all these other forces are just canceling out. And that's all divided by 40. I'm about to get an acceleration. And it's a modest 0.82. But again, I'm not even circling the answer because I don't want like all this extra emphasis I don't want this extra emphasis on the answer. What I want to emphasize is the net force came from here. The net force came from that force diagram. And in that force diagram, you can see that it's the horizontal forces that are really determining this acceleration. So I know I can just do my horizontal component minus the friction. Horizontal component is 93, friction is 60.2, and I get an acceleration of 0.82. So we can see this is really all about the force diagrams, so we can figure out our net forces. You got a lot going on here. Here's a quick summary. This is what if you push down on something on a surface, you increase the normal force. Here's that weird idealized scenario where you just have one force magically. Here's probably pulling on something on a surface and there's maybe some friction. Doesn't fully cancel it out, so it's still accelerating. This is accelerating down in an elevator. This is standing on a surface or maybe moving at constant velocity in an elevator, or you could be standing on an escalator. Could be any direction of velocity because that's equilibrium right there. This is accelerating up in an elevator or some such situation. This is either pushing on an object with static friction typically, or you're just moving something along. And this is a totally different scenario that has yet to be seen, where you actually have an object on a surface going like this, and then it is sliding down the surface, and there's a component going like so. And these two forces are equal. There's my normal force away from the surface, my component of the weight into the surface, and then let's say that was a 60-degree angle. Here's my 60-degree angle right there, and we'll get into that more later. But this has been Turgeon bringing you physics from afar.